Welcome to lesson 6.3, angles inscribed in circles. So obviously we're looking at angles in this lesson, but we need to make sense of what does it mean to be inscribed in a circle. So our first vocabulary piece, an angle is an inscribed angle in a circle if and only if the vertex is on the circle and each of the angle's sides intersects the circle at a point other than the vertex. So for example, we'll look down here. Angle CBD is an inscribed angle. The vertex of B is on the circle and its other two points are on the circle, not the same as point B. So if we'd extend this side forever and this side forever, they intersect the circle at two different points that are not the vertex. So this is what an inscribed angle looks like. Every inscribed angle intercepts an arc. An angle intercepts an arc, forming an intercepted arc. If the arc, except for its endpoints, lies in the interior of an angle. So what's an inscribed arc? So if we're looking back at this angle, angle CBD, arc CD right here, this arc along the circle, is an inscribed arc. It's the arc piece in between the 2 points of the inscribed angle. And another piece of notation, just to make sure we know it, a zero-looking shape with a dot in the middle is a symbol for a circle, and the letter next to it tells you the center point. So this symbol here, the circle with the dot next to the letter A, means circle with a center point of A. So now that we have the vocab, let's start to look at some of our theorems and properties. So the inscribed angle theorem simply states the measure of an angle inscribed in a circle is half the measure of its intercepted arc. So if we wanted the measure of angle CBD, it would be 1/2 times whatever the measure of arc CD is. So it'd be right here. Angle measure is half the measure of the inscribed arc. So an example of that would be here. In the figure below, T, P, and Q all lie on circle M. If the measure of arc, TQ, is 48, find the measure of angle P. So our TQ is the inscribed arc of angle TPQ. So the measure of angle P is half that measure of arc TQ. 1/2 of 48 gives us a measure of angle P being 24 degrees. Now we can look at it kind of in a different way. Example 2 here. What do we know about circles? Well, we know a whole circle measure is 360 degrees. So a semicircle, for example here, from M to N to P, that major arc, MNP, would have a measure of 180 degrees, definition of a semicircle. So we know M to N to P, or P to N to M, that major arc is 180 degrees. What also they told us is explain why the measure of angle N then is 90 degrees. So definition of a semicircle we knew was 180. That's where we needed to start. We know the measure of angle N would be half the measure of MQP, this arc here. Because angle N is an inscribed angle, so the inscribed arc would be P to Q to M. Well, we know PQM is a semicircle or 180 degrees. So half of the 180 would give us the measure of angle N, which would be 90 degrees or right angle. And then example 3. What they tell us is in circle Q, the measure of arc RV was 110 degrees. So R to V here was 110 degrees. From V to T, this piece down here, was 50 degrees. And the measure of angle SRV, this inscribed angle, was 55 degrees. Find the measure of arc SR. So we're looking for the measure of the arc S to R here, this question mark. So what do we know? We knew that SRV was 55 degrees, that angle. So that tells me the whole arc that angle makes, arc STV here, has to be double that angle measure. So S to T to V had to be 110 degrees. So if STV is a 110 degree arc, minus the part we knew, arc TV, that would leave us with arc ST right here. And arc ST, 110 minus 50, is 60 degrees. So now I know 110 degrees, 50 degrees, and 60. Arc SR makes up the rest of that circle. So we can simply do 360 degrees in a circle minus these 3 parts to find out what SR's measure is. So 360 minus these 3 added up, which is 220, gives us the measure of arc SR is 140 degrees. And then we get into example 4. Example 4 says in the figure at the right, segment TV is the diameter of circle O, and R and W are points on this circle. Explain why the measure of TRV is 90 degrees. So similar to the one that we did up here with angle N in example 2. So almost the exact same concept. We know that angle TRV is creating the inscribed arc of TWV. So TRV gives us the arc of T to W to V. TWV is a semicircle, so it measures 180 degrees. So again, the measure of that angle, TRV, is half the measure of the arc, which tells us the measure of angle TRV has to be half of 180, which is 90 degrees. And the reason we're revisiting this is because example 4 is supported by Thales' theorem, which states if an inscribed angle is intercepting a semicircle, then that angle is always a right angle. So any inscribed angle that creates an intercepted arc of a semicircle, that angle is always a right angle. So we can use that concept in our last few examples here. Example 5 tells us points B, C, and D are all on circle O. P is a point of circle O, but not on arc BCD. And the measure of angle BCD is 140 degrees. Find the measure of arc BCD. So draw what we know, and over here is what we know. We had circle O, we had B, C, and D on the circle, and then we had point P, which is not within that arc of BCD. Arc BCD was 140 degrees. So the arc intercepted by angle BCD here, creates this whole big arc of BPD. So in this case, we know that the measure of angle BCD would equal half the measure of that arc, BPD? Well, BCD was 140 degrees. So if we double that, we get the measure of the arc it creates. So arc BPD was 280 degrees. So 360 minus arc BPD, which was 280, leaves us with 80 degrees, which is arc BCD. So 80 degrees would be the measure of arc BCD. And then our last example, example 6 here, says 5 points on a circle at the right are all equally spaced to form congruent arcs, and they're connected to form a pentagon. What is the measure of each interior angle of this pentagon? So we know in this case that 360 degrees, our whole circle, is being divided into 5 equal parts. So 360 divided by 5 tells me each arc around this exterior is 72 degrees. One angle of the pentagon is an inscribed arc made of 3 of the 5 congruent arcs around the exterior. Because if I drew in one inscribed angle of this pentagon, from this point to this point, if I go around my circle, it'd be 1 arc, 2 arcs, 3 arcs. So that tells me 3 times the 72 would give me the measure of those 3 arcs. So if I want the measure of the angle, it is simply 1/2 of that. So 3 times 72 gave us 216 degrees for this inscribed arc. If we divide that by 2 or multiply it by 1/2, we get the measure of the angle, and that angle is 108 degrees. So each interior angle of this pentagon with congruent arcs would be 108 degrees. Now we can check that using our interior angle rule of a polygon. N minus 2 times 180 would give us the total of the interior angles. So 5 minus 2 times 180 is 540. Now if each of these sides are congruent, 540 divided by the 5 sides tells me 108 degrees for each angle. So our proof here, kind of a written out proof, I should say, is supported by one of our theorems from last chapter. So in this lesson, the big idea can be all the way back to this inscribed angle theorem right here that the rest of the math in the lesson is based on.